This is kind of like not related to this direct section, but with regards to project 4, yeah, there's quite a bit of time to do it. It's due at the end of this month, tentatively. So I would definitely there's one part of it that like you don't really get to until the next couple of lectures, which is like how to deal with parallelism and optimization and speed up and whatnot. But I would say if you have the time and the bandwidth, definitely like take a look and start working on the first 3, because first one is just doing regular matrix multiplication. And the second part is building like the Python interface between the C and Python kind of like testing framework. There's a lot of infrastructure that like is already given for that. So I would say just like sort of follow along with that and you'll be fine. Matrix operations, typical kind of C stuff. Make sure you're focusing on your pointers and keeping track of them. And hopefully you guys gotten a decent reprieve from C so far. So it's a nice kind of going back into it, but not supposed to be too difficult. Yeah, and then part 4 is mainly like the speed up portion, which is you're going to be using like the different components that we talk about. Like for example, discussion, or in this section, we'll be talking about caching and like blocking and like how to optimize like those kind of things as a general idea. So I'm using that as well as the other tools that you'll see later. Okay, so we're going to get started. Looking at the kind of the section check-ins, it seems like in general, like misses and TIO breakdown have like a kind of equal sort of like coverage. And then we're going to be talking about multi-level caches and then AMAT as well. We got to talk about all of them actually last section. So hopefully that trend continues for this one. Just as a general kind of a reminder, sorry. The whole caching system, basically the purpose of it is to reduce the amount of overall headway time-wise with regards to everything else, because accessing main memory just as a whole by itself is not very good. So the time for that is just not efficient. So if we do that for every memory access, then it's quite inefficient. So caches kind of give us a bridge between direct register storage and then this. So we'll see later for multi-level caches, like within the caching kind of system, there will be different levels as well. So like bridging the first level cache to the memory, there'll be second level, third level, and fourth level. So most of your laptops, if you go into the specs and look at it, you'll see that they're different sizes up to until 4 caches usually. Sometimes others will have more, but at that point just kind of gets redundant and doesn't really make a difference. So typically it's capped at 4. Okay, so kind of breaking things down, the very first item that we're going to talk really quickly about, there's not really any direct questions with regards to this section, so I'm just going to talk about it. The 3 misses that we're going to talk about mainly so far in this class are going to be compulsory conflict and capacity. There is a 4th miss that we'll talk about later on, coherency misses. That has to do with when like different caches start to conflict with regards to like them being updated and whatnot. So that'll be touched upon later on. So far, we'll have to worry about this. So looking at this, the idea of compulsory misses is like it has to happen basically. This happens basically when a block is first loaded into the cache. So this is like, regardless of how full the cache is, compulsory misses, if it's the first time we're loading a block, it's always going to be compulsory. Even if it's like one of the other ones, it's still going to be categorized as compulsory. So this happens when block is first accessed by cache. So the solution to this, the official solutions are NA, like there's no solution. But if you were in discussion, you'll have seen that there's like actually kind of something special that you can do. So what you can do is, it's called the kind of preemptive loading. I think there's another term for this. I'm kind of blanking on what it is at the moment, but I think it was like predictive something or another. But basically what this is like, in RISC-V, when we're doing pipelining, we saw that there was a situation where like, well, if we don't branch, then we're going to continue. But if we do branch, then we want to flush and then load this stuff afterwards. So it's trying to predict what will the next lines be. So what will the next accesses be? This is the same kind of idea. The system basically says, well, we're currently accessing a particular address. I'm going to try to guess what your future accesses are going to be. I'm going to load them while you're accessing the old addresses. So while we do that concurrently, it's going to save us to access time. So we don't have to wait if we're right. Obviously, if we're incorrect, then we have to load the new thing in and evict whatever old block. So there is a penalty for messing up. But usually the system is pretty good in terms of predicting this, so it'll work actually decently effectively. Theoretically, we have a perfect preloading system. It's actually going to give us 0 compulsory misses because everything will have been loaded at least a couple steps in advance. So we never wind up having a compulsory miss. Obviously, nothing can be perfect, so which is why even for the most optimized system, you're still going to have a certain miss amount. So conflict miss, what this is referring to is basically, well, if 2 addresses have the same index, then we're going to cause a conflict miss. So this is with 2 distinct addresses, so 2 addresses with different tags. The reason for this is because it's not necessarily the case that the 2 addresses will map to the same block. It's that they'll map to the same the set. And so this is important to note because well, this we'll talk a little bit more about this later on with examples, but we have our direct map cache, which is also going to be considered a one-way set associative cache. So set associative. What this basically means, oh my goodness. What this basically means is that for every index that we have, there is going to be 1 block that corresponds to that index. So only 1 block can fit within this set. So more commonly, what you'll see is an n-way set associative, with n being some value, set associative. And what this means is for every index that we have, we're going to have n blocks that can map to this section. So it's almost like a hash map in that sense. For each hash map, we have an index. And then we have some linked list that follows with the values that can come after it. So in this case, it's very much the same idea. The only difference is there's a limited quantity, and for every single index, we have the same quantity that can map to it. So typically what we have is the usual optimal number we'll have for n is going to be 4. That's typically pretty optimal. Any more, you can technically make it work depending on the machine, but this is pretty standard. The last one that is actually quite interesting is the fully associative cache. And so this is basically saying, okay, fully associative. This is basically saying we have 1 index, which is just 0. So effectively no index at all. And then instead what can happen is we're going to have k blocks, with k being the total number of blocks that fit in the cache. So well, we can also call this k-way set associative with k being equal to a cache size divided by block size. And this gives us the number of blocks. So the reason that this is important to know is because in most standard units of hardware, you won't actually have fully associative cache because something that has to be done is you will have to have hardware to be able to compare every single pair of tags. And that's going to be 2 to the n number in terms of, forgot the term, in terms of asymptotics. And that's just going to be really, or sorry, n squared, yeah, n squared. And that's just going to be really, really bad in terms of expensive hardware, a lot of overhead for comparison time, and it just negates the purpose. So you'll really only see a fully associative in theoretical senses, as well as in the TLB. So TLB is basically the cache for virtual memory, which we'll talk about next section. So yeah, for conflict misses, it's going to be 2 distinct blocks mapped to same set, so set/index. So the way that we fix this is basically by increasing associativity. So you might have remembered if you were in discussion or looked at the discussion questions, there was one way that's oh, you can tell the difference between a conflict miss and a capacity miss by basically pretending that the cache is, everything is the same aside from the fact that now it's going to be fully associative. If you still have a miss regardless, it's going to be capacity. But if you no longer have a miss in that kind of circumstance, then it's going to be a conflict, because all it means is that you have extra space, you're just not utilizing it because 2 blocks happen to be mapping to a particular section that has a that already has something there, so you have to kick it out first. The last one is the capacity miss. So we're going to use yellow for that, or orange. Capacity miss is basically not enough space. So cache ran out of space. Cache is full. And you can tell this basically by increasing associativity. The only way that this can be solved is by increasing size of cache. Are there any questions for this section? Okay. Real quick for anyone who joined a little bit later, If you didn't fill out the kind of check-in form, here it is linked in the chat. It's just used for so I can check in with you guys if anything's going on, and you can let me know if you want to talk or like cover specific aspects. So yeah, stuff like that. Just a quick reminder, there's no if anyone ever asks or a question asks oh, what's the best caching system? There really is no best. It will depend on your code, your program you're trying to run, your system, as well as a lot of different other factors. So oftentimes there will be sort of a combination of ways in which that you can combine these different factors to optimize your cache, which or optimize your program to your cache or vice versa. Okay, so we're going to briefly talk about TIO really quickly. I'm going to talk briefly about what TIO is, and then we're going to jump actually to the multi-level caching system to get practice with that. So just a quick reminder, TIO, what it stands for is tag, index, and offset. So this is broken down from when you're given a particular address. So it's not a new number that you generate. You just take the bits from the address and then translate into this breakdown. So the way that this breakdown works is usually we start with the right-hand side. So it's ordered in this way, but we always start from the right hand, or not always. You can do either of these two first. You can't really do this one first. But the offset is the easiest to calculate because all it's saying is I have a page and my data is sitting at a particular index on that page. I want to know what data it is. So the offset basically gives you the index within the block. So the way in which you calculate the number of bits needed for the offset in a particular address is the log base 2 of page size. And the reason for this is because the pages are going to be byte address, which means that for every particular bit or byte that you're trying to access, you need a new index. So for all of them, the page size is going to be X number of, or N number of bytes. So to figure that out, you have log base 2 of N. Similarly for index, what you're trying to calculate is basically how many indices do I need for all my sets? So effectively, how many sets do I have? To calculate this, what you have is you're going to have log base 2 because we're trying to figure out the number of bits. And then to calculate the fraction, what you wind up having is the cache size. So cache size, then you divide it by the block size. So far what you end up getting here is the number of blocks that you'll need. But we're actually more focused on sets because it's not always the case that it's going to be direct mapped. So to calculate that, then we multiply this bottom by the set number, not set number. We're going to say n, with n being in an n way a set associative cache, the n value. So it's how many blocks can fit in a particular set. So this overall fraction gives you the number of sets overall that you'll need. And then for the last part, for the tag, essentially what it's doing is it's identifying the unique block. So if you have the same index and then you only have the offset, you can't tell if it's the same or not, because within the same block, you can have the same, you're going to have the same index, and you can have different offsets. That doesn't tell you very much. But even if you have the same same I and O, index and offset, it's not guaranteed that it's going to be the same block. So we use the tag bits in order to be able to tell which one it is. So to calculate that, we have our overall address size, so address length in terms of bits, and then minus the I bits and minus the O bits. So a real quick thing to note is when we're talking about cache sizes, we're only talking about the data cache, which means the stuff that we load in. The I is already kind of built in because it's going to be our indexing system. And then the O is also built in because we're indexing into our blocks. The only thing that really doesn't get accounted for is the tag bits. So the question then begs, where are they stored? Are they considered part of the cache size already? They're actually not. So they're going to be stored out elsewhere in sort of a meta cache sort of place. And you don't really have to worry about how it's stored or what it's doing. But basically, all you have to know is when we're doing the comparison, you're taking the tag bits from that kind of meta place, and then you're comparing it to the new one that you're loading in. If they're same, then cool, you're all good. It's the same item. If it's different, then you got to evict something based on whatever policy you have, and then boot in this new one. Okay, real quick, are there any questions for a TIO breakdown? I know that was really, really fast, so I'll give you a couple seconds to kind of process everything. Okay. If there are no questions, I'm going to really quickly just go through a direct map to examples just to kind of demonstrate the breakdown. So, and then we're going to hop into the next section. So first things first, when we look at this, we have a 4 KB byte cache and 250 56 byte block. So right now we can automatically figure out, well, we know the offset bits. So the offset bits are going to be the least significant bits. So in this case, our n is going to be our log base 2 to the 8, because we know that 256 is 2 to the 8. And so that's going to give us 8 bits that we need. And then so we're going to try to figure out our indices. So to get that, we have log base 2, and then we have, well, our overall cache size. This is going to be 2 to the 12 because it's 2 to the second times 2 to the 10, which is the KB byte part. This is part of the IEC prefix system. So if you feel uncomfortable like converting between this and like regular kind of like kibbies versus like the actual number of bytes, I would suggest you do some of the practice from discussion 1, not section 1, discussion 1, because that's where the practice problems for the conversions are. We use this mainly because it's a lot more useful just in terms of categorizing things and to count things, and you'll really quickly see why we don't use 10 to the anything, which is like the kilobyte, gigabyte kind of system. Just as kind of a warning, there's oftentimes like people will like basically say like these two are the same thing. And basically they mean that like this is going to be referring to KB bytes as well. So it will become confusing after a while. If you're not sure, just always clarify. But we'll in 61C, we'll always be using this kind of system. So okay, that was a kind of tangent. So going off of this, then we have log base 2, and then we have 2 to the 12 divided by our page size, which is 2 to the 8 times our set number, which in this case is going to be n equals 1 because it's direct math. So times 1, this is going to give us 4 bits. And then so what's left for our tag bits is going to be, so tag is going to be equal to 16-bit system. So 16 minus 4 minus 8 is going to give us 4 bits. So our TIO breakdown is going to look something like 4, 4, 8. So in terms of the indices of the bits, we're going to have 0 to 7, 8 to 11, and then 12 to 15. Are there any questions for this? So yeah, the 16 from the tag is just because right here we have assume we're using a 16-bit system, so it gave it to us. We'll see like later on. Typically what it says is like, oh, we have a memory space of something IEC prefix, insert IEC prefix here, and then bytes. So based off of that, we typically won't say, oh, assume this for the address size. You'll have to calculate the address size for yourself. But yeah, this one, they gave it to us. Okay, if there are no questions, I'm going to skip this section for now. I would say come back to here if you're feeling a little uncertain about the types of misses that you'll wind up having. But we're going to jump to part 3 for a second. So I'm going to give you guys about 2.5 to 3 minutes to work on this 3.1. This is just a first level kind of cache, or sorry, this is a single level cache. So nothing too special about it, just practicing TIO breakdown. So and then we're going to hop into 3.2. So if you have time, I would say look at 3.2 and 3.3, 3.4. They're all quite similar. So I'll give you guys about, say, 2.5 minutes to work on this. And if you feel like we need more, we can always add time. So let me find the music. I also realized I'm really dumb. I should have recorded this to the cloud. I don't know why I keep on recording locally. I am stupid. It's fine. or so. Okay, I'm going to start going over this just so we can hit the multi-level caching and the rest of the information. Okay, for this first one, what we have is looking through some of the information that we're given. We have a 8-way set associative cache. So this gives us information that n is going to be equal to 8 when we use it. And with 512 bytes of data, so this we can translate to 2 to the 9 bytes for future use. This is our cache size. The size of each block is 16 bytes, so that's going to be useful. This is 2 to the 4 bytes. And then there are 8 MIB bytes of main memory. So this is the key part. Usually we won't give you the address size because it'll really differ depending on the machine. So we'll give you just how much main memory there is. So like this is also kind of a tangent to a virtual memory portion where we'll say, oh, physical memory is this size, virtual memory is this size, and then it'll be up to you to figure out, well, what does this mean in terms of the address size? So given the fact that we have 8 MIB bytes, this means that, so for this is going to be 2 to the 3rd, which is the 8 part, times 2 to the 20, which is going to be the MIB byte part. So that's going to give us a total of 2 to the 23rd bytes worth of memory. So as we know that all memory in 61C is going to be byte addressed, this means that, for every single byte that we have, we need a new index. And for every index essentially is going to be an address. So like addressing is basically indexing through memory. So that means in this case that we need an address or an address/index for every 2 to the 23rd byte. So to figure that out, we have log base 2 of 2 to the 23rd. Again, why IEC is useful. And then we have, that means we have 23 bits. So just really quickly imagine if this said like 8 megabytes worth of memory. Like just imagine that. Then this would give us like what, 8 times 10 to the 6th bytes worth of memory, and trying to do like log base 2 of that, like that's just gross. So that's why we don't use the standard kind of prefixes. Or not we, I guess, as a system sort of like whole. The lower you get down into the more you're going to end up using the IEC kind of as opposed to the more commonly known ones. Okay, anyways, going through that. So the first thing that we want to solve is our offset. So our offset we know is going to be log base 2 of whatever we're given right now. So that's 2 to the 4. So that's going to give us 4 bits. And then for our index, what we have is we want to calculate log base 2 of our cache size, which is 2 to the 9 bytes, and then divided by our block size, which is 2 to the 4, times our set size, which is 2 to the 3, because it's 8 right here. So that's going to give us bottom of 7 and up of 2. So that's going to give us a total of 2. So this is log base 2 of 2 to the 2nd. So that's going to give us 2 bits overall. So to figure out the tag bits, then what we have is we have our 23 bits that we calculated earlier, minus 4 for offset and minus 2 for index, which is going to give us a total of 17 bits for the tag. Are there any questions for this part? Okay. How do you guys feel just like a sort of sanity check? Like, are you guys feeling okay? I guess put a for reactions, put a thumbs up if you feel okay. Or actually put whatever mood that you currently feel. I wish there was a sad one, but there's not. Okay. Okay, hopefully in general things are time-wise, like it's going kind of okay. Yeah, let me know if you want me to repeat anything or if I should slow down or whatnot. Okay, So kind of then going through the rest of this, what we have is, well, okay, the next portion is talking about two levels of caches. So now we have, suppose we have a machine with two caches, L1 and L2. So L1 is always going to be higher than L2, which means that it takes less time to access, but it's going to be more expensive. So both caches are direct map caches. The L1 cache can hold 256 bytes worth of data. So as we can see, L1, because it's higher up, more expensive, yada, yada, it's going to be smaller than L2. So L2 is going to be able to hold 4 kibibytes. So a very significant difference in terms of how much we can hold. Assume the following code is written or run on this machine. So then the questions gives us, this produces a hit rate of 7 out of 8 for the L1 cache. So that means 7 hits out of 8 accesses for L1, and then 3 out of 4 for L2. So for this, then we have 3 hits per 4 L2 accesses. So this is per 8 L1 accesses. So something that's important for this particular problem is to note that only the misses in L1 go to L2, because otherwise it's going to be redundant. So so basically, if we miss in L1, then it's going to go to L2. And then because we're able to load more into L2 at a single time, then it allows us to basically have more breadth. Given that the array is a block line address and size of UN16T is equal to 2 bytes, what's the block size of L1 in bytes that produces its hit rate? And then for part 2, using variable y to represent the answer, what's the block size of L2 in bytes that produces its hit rate? So express your number as a function of y and not as a number. Just do both. Just do both. It really does not matter too much. One thing I would pay attention to is look at which part is the looping part and then how it's being accessed. So looking at that as well as the different parameters we were given, I would say that is how the best way to solve this problem. So I'm going to give you guys about 5-ish minutes to work, or let's say 4-ish minutes at first, and then we'll reevaluate how we feel. Yeah, and I feel like tired is just everyone's constant state of being at this point in the semester. Hopefully you guys can get some rest this weekend. Also, just like as an FYI, I'll be driving like very shortly after this. So I don't know if I'll get the chance to upload the recordings before I start driving, but I'll upload them tonight, and I will send the solutions and notes as well as I'll send the solutions and notes first, and then I will figure out the upload and then send that afterwards. So just to let you guys know. Okay, probably another probably a minute or so, and then we're gonna try to go over the answers for this. Okay, I'll start going over the answers for this. Is that okay with you guys? Yeah, hopefully. Okay, so for this section, a couple of things like I said earlier that was important. So we want to focus on two main things. So for L1 cache, what we're looking for is, well, two things that we need, that we know. So we have the number of accesses that we care about right now are 8, so a cycle of 8. And then so for all of those, we have 7 hits and 1 miss. So kind of like a standard thing for an array. We know that this array is block aligned, which means that the first element of each of the array is the start of a block. So that means we know that our very first access should be a miss, which means that the next 7 are going to be hits. So then looking at the way that the array works itself, so we know that there's only going to be one access during the loop itself, which is this read right here. And so that means that for our total number of accesses, that means we have to do this loop 8 times in order to have 8 accesses, which also means that we're going to be accessing 8 different values. And so we're not accessing the same value twice. So that means the overall block size, what we're able to load is going to be 8, which is the number of accesses that we have, and then it's going to be multiplied by the size of whatever values in that address or in the array. So in this case, our array is our UN16T, which we know from earlier is going to be 2 bytes. So our overall block size is going to be 16 bytes. Are there any questions as to how we got that or how we got there? Sorry that like my face is in shadow. I don't know what's up with this light. It's making me like no one can see anything. But anyways, okay, if there are none, then we're going to move on to the second part. The second part is essentially the same. The biggest difference is the fact that we're not looking at every single access. We're only looking at the only ones that, again, that get passed into the L2 level are the ones that missed on L1, which means that we're going from 3.3, we know that it's going to be in every 8 values is going to be a miss. So every 8 values, so every block of L1 that passes into L1 cache, we're going to have a miss that gets passed into L2, which means that for each of those sections, they're going to have to essentially either hit or miss in L2. So knowing L2, we have 3/4 for a hit rate, which means that for every 4 accesses in L2, we're going to have 1 miss, which means that that's going to be the one that loads the particular block for L2. So that means that we're going to have 4 L2 accesses, which is going to be a total of 32 L1 accesses that we're going to have that pass on to L2. So in that case, like then our immediate kind of thought is like, okay, well, it's going to be 4 times y, which in this case is going to be 64 since it's 16. So if we go backtrack and sort of think about that, if we load a 64 byte block, we're going to have access to 32 values. So the only values that really matter to us are at 0 and then 32. 0, 16, 32, and then 48, because I can do math, and at 48. And the reason for that is because those are the ones that missed in L1. So that's why we know that a 64 byte block for L2 makes sense. Are there any questions for this section? Feeling okay about L? Are there any, I guess also like conceptual questions about like why maybe if we need like different levels and whatnot? Okay. If not, then we can really quickly, we're going to skip over 3.5 and 3.6 right now because they have to do with AMAT as well. So we're going to briefly talk about the idea of AMAT and what it really is. So AMAT stands for average memory access time. And so this basically is saying, well, if we try to say like, oh, for any memory address, how long is it going to take like for this particular access? We can't actually say that for with a guarantee because it could be an L1 cache, in which case it would be very fast. It could be an L2, which is going to be slightly slower, L3 slower than that, L4 slower than that, or it could be in main memory, which is going to be quite slow, like going to Sacramento. And then, or it could be in the disk, in which case it's going to take absolutely eons to load. So like it's going to take different times depending on what the current state of your cache is and what your access is going to be. So instead of doing that, we're going to have our average time. So to calculate the average time, we have to factor in all of these different levels. So the overall AMAT equation is going to look something like this. So it's going to be the overall hit time. So for whatever level, like highest level that you're currently at, and then you're going to take the miss rate for that particular level and then multiply it by the miss penalty for that level as well. So 4 level. What this means is, for example, if we only have one level of cache, our miss penalty is going to be the time that it takes to go to main memory, because if it fails on the first level, then it has to go to main memory. But say if we had multiple levels, like say if we had 2, then our miss penalty, so like say for one level, then it would be main memory access time. Say if we had multiple levels, then what the value ends up being, so like say in this case we have 2, it's going to wind up being the hit time for L2, and then plus the miss rate for L2, and then times the miss penalty for L2. So depending on how many levels you have, then the miss penalty kind of goes recursively on from that. So this basically takes into account the amount of misses that we have, as well as how what we're going to lose if we take that miss. So we're going to apply it to the first question right now. So, or first two. I'm going to give you guys about, let's see, 4 minutes again to work on this. So for parts 1 and 2, if you get through it and you're done, feel free to go back up to 3.5 and 3.6, as it's quite a similar idea. So I'll give you a couple minutes. I have to also briefly use the restroom, so I will be back in a second. Hopefully this screen doesn't die. Let me like keep something on it so it doesn't die. So probably about 2 more minutes on this. Okay, so we're going to start going over the question or these 2 questions. So these two aren't like terribly like awful. They're not supposed to be like terribly awful in terms of what questions they're asking for AMAT. They're pretty standard questions that you might see on homework, possibly exams, possibly with like a little twist to it. So if you understand like the concept of this, then you should be pretty good for like any AMAT related questions. If you're feeling still a little iffy on it or not sure how it works, that's totally fine. That's what these practice problems are for. Okay, going through this, a couple of things that we want to make note of first. So we have an L1 cache with a hit time of 2 cycles. So that means it takes 2 cycles of time, even if it works. And then, so L2 cache with a hit time of 18 cycles. So as you can see, it's quite a deal slower. And then overall, we have the L2 cache has a 15% local miss rate and a global miss rate of 5%. So if the main memory accesses take 60 cycles, as you can see, a lot slower, what is the AMAT for its caching hierarchy in clock cycle? First things first, we want to know the L1 miss rate because that's how like often we'll have to approach like the L2 in order for that to happen. So this doesn't actually directly give us that information, which is quite interesting. So looking at this then, we want to actually figure that out. So we'll use the local miss and the global miss kind of idea. So from earlier, I don't think I'd actually talked about what the difference between global and local miss rates were. So like a miss rate overall is just like miss rate overall is number of misses per some number of accesses. And similarly, like hit rate is like the opposite of that. So same, but with hits. So basically they're going to be like one minus the other one for itself. So for miss rate overall, what you'll have is you'll have a global miss rate as well as a local miss rate. So the difference between this is like the scope of what you're looking at. So this is always going to be in context of like a particular level. Because if you only have one level, the two values will be equal. So for global miss rates for any particular level, it'll be number of misses on that cache level divided by number of overall cache accesses. So for all particular levels. Whereas local is going to be slightly different. It's going to be basically the same thing. But what we have here is we're going to have number of misses on that particular cache level minus number of cache accesses on that level. So as an example for this, like what we have here, I'll zoom out by the way afterwards so you guys can write that down. I'll also email you guys the notes for these. So like we have a 50% local miss, which means that it's going to be some number of misses divided by the number of local accesses. So like for L2, whereas the global miss rate is a lot lower. You'll see as this is the number of misses we have in L2 divided by the total number of accesses we have. So we can actually use this to figure out our L1 miss rate. So our L1 miss rate is going to be something quite interesting. So if we look at these two values, basically, if we want to figure out, well, the values that we want is the number of cache accesses on L2 level divided by the number of overall cache accesses. And the reason for that is because, well, it's only the ones that are going to be on L2 are the ones that were missed in L1. So to get that, then what we have is we want to have global divided by local. So to calculate that, we'll have global miss rate divided by local miss rate. And that's going to get us 0.05 divided by 0.15, and that's going to come out to be 1/3. So now to calculate overall, the value will be AMAT, so it's going to be equal to, so our very initial level is going to be L1 hit, so it's going to be 2 cycles, plus the L1 miss rate, which is going to be 1/3, times the L1 penalty, which means that we're going to be going to L2. So on L2, the hit rate or hit time is going to be 12, and then we're going to add the amount of misses, the miss rate that we have for L2. So for L2, we have a miss of 0.15 because it's the local miss rate. Then we're going to multiply it by the penalty. So basically what happens if you miss in L2, which means that we have to go to main memory. So that's going to take 60 cycles. So calculating this, we have 2 plus 6, or sorry, I can't do math. 2 plus 4 plus 5 over 100 times 60. So that's going to get us to be, so this is going to go out. This is going to be 30. So we all have a 3 here. So this is going to get us a total of 11 cycles. So that's on average how long it's going to take, which is quite, like, it's obviously not going to be 2, but it's also less than L2's time, and it's also significantly less than main memory. So you see how the different levels really affect the values in which that you get. Okay, so that was kind of a lot. So let me zoom out. So if you guys need to copy anything down. Are there any, do you guys have any questions about just overall? Because we have about 2-ish, probably 1.5 minutes left. I can't stay over time today, unfortunately, but do you guys have any questions overall about caches as a concept? Anything in particular, anything about class itself? Or any potential like things that you want me to answer? Okay. If not, then we just hit 59. So I'll let you guys go about a minute early. Just, it's one of those days, I feel like. It's also that kind of point in the semester where everyone's just tired constantly. So yeah, good luck on finishing Project 3B if you haven't yet. Get started on Project 4, I would say. And yeah, good luck on everything. If you need to talk or check in, be sure to email me. I have seen the emails, by the way, for anyone who's already sent them to me. I just haven't had the time to respond. I'm really sorry. Yeah, stop the recording.